Hello, in this video we will present our thesis titled Boundary Layer Control Methods. This thesis was done by Julian Efraín Marin Olivas and Ruben Alejandro González Pizarro. To start, research in the aerospace field has many different areas of study, but most of them are centered on the optimization of the aircraft by different geometries or different materials to use. Within the optimization, the study of the aerodynamic forces is one of the most important since it will determine the efficiency of the aircraft. Thus, this study will be centered on a review and a comparison of the multiple boundary layer control methods which increase the efficiency and control of an aircraft. Following researches about this theme and completing a list of advantages and disadvantages of each of the methods will be mentioned. This research will be focused on the turbulent boundary layer control, which we will explain what it is later. The study of the fluid has been an important field in science with so much to learn and so much to improve. A certain methodology to understand the description of the fluid motion was to focus on a perfect fluid, meaning an incompressible and non-viscous fluid. With this description, researchers were able to get a very specific description of the fluid motion. Nevertheless, this description, as mentioned before, didn't include the viscous property, thus it didn't express certain things as the skin friction drag. That is why the objective of new researchers was to focus on the motion of that non-perfect fluid. With this in mind, when a fluid is analyzed considering the viscosity, we can express how the fluid will behave and predict things like turbulence. Focusing on this, we can start by giving a definition to our main theme, which is the boundary layer. To give a definition of the boundary layer, we first need to try to explain the behavior of the fluid near a surface. A viscous fluid will have some friction forces when the fluid passes through a surface. That is why exactly at this surface, the fluid will have a velocity of 0. The distance between the surface of velocity 0 and the start of the true speed velocity will be a small layer which will be named boundary layer. There are two types of boundary layer which depends on the Reynolds number. The Reynolds number can be defined as the ratio of the inertial forces to viscous forces. It is used to categorize the fluid systems in which the effect of viscosity is important in controlling velocities. So if the velocity of the fluid reaches a certain Reynolds number, it will determine the behavior of the fluid, naming it laminar or turbulent flow. Thus, we have two different types of boundary layers, which will be laminar and turbulent boundary layers. We will focus on the control boundary layer during turbulent flow, which can be expressed as random and non-linear. The boundary layer can be controlled by different methods, some of which will be mentioned in this research, therefore improving the aircraft performance if the method is valid. We will be reviewing 5 different methods for boundary layer control. Okay, so we're gonna start with the methods. The first one is turbulent boundary layer control with Lorentz force. The goal of this method is to impose the Lorentz force generated when an electrical conducting fluid flows through an electromagnetic field along the flow direction. This imposed force has been intended to delay the transition between laminar flow to turbulent flow, with the boundary layer becoming more stable. This stability is accomplished by an alternating array of electrodes and magnets. This procedure will be centered on drag reduction, by disturbing the semi-equilibrium state between the near-wall streamwise vortices and the wall. This method postulates that the most effective way to achieve the drag reduction is to introduce the Lorentz force perturbations be perpendicular to the forces. The required Lorentz force will be created by placing electrodes and magnets side by side, parallel to one another, as shown in the image. The results were applied for different oscillation periods and with a Reynolds numbers of 100. With this taken into account, the results show a decrease in drag for an oscillatory period of 100, but not for 500. It is demonstrated that a Lorentz force produced by strips of magnets and electrodes with a reasonable magnetic field strength and voltage can create sufficient perturbations parallel to the wall and perpendicular to the near wall streamwise vortices, such that the skin friction drag is reduced by approximately 40%. Unfortunately, accounting several methods using the Lorentz force, it requires great cost of input power to accomplish skin friction drag reduction. Taking into consideration the power required, this method is not considered as practical. The next method is called directed synthetic jets. The synthetic jet consists of an orifice or neck driven by an acoustic source in a cavity, as shown in the image. With high levels of excitation of the acoustic source, there is a stream of flow that emanates from the neck. This synthetic jet is embedded in the wall of the boundary layer, for which separation control is desired. In resume, on the in-stroke of the neck velocity, vertical momentum is imparted to the flow, causing a preferentially ingest approaching low axial momentum of the incoming boundary layer. On the outstroke, due to the curved neck, the fluid particles are reaccelerated and injected with positive axial momentum into the wall region of the boundary layer. Both the in-stroke and the outstroke of the cycle increase the ability of the boundary layer to resist separation. With this conversion of acoustic energy into the mean flow increasing the time average axial momentum of the boundary layer, thus making the boundary layer more resistant to separation. Within the simulation results show this method is very practical considering the power required for this acoustic device. A simple model was introduced with great results demonstrating the practicality. The next method will be local heating. This study is carried out because the exploration of practical methods for friction reduction in turbulent boundary layers is of great importance, and strategies that are easy to implement and have wide usage are particularly desirable. Several studies have investigated the effect of wall heating on the linear stability of laminar flows with temperature-independent viscosity. The linear analysis predict that heating has a stabilizing influence on flows and thus provides a possible strategy for transition delay. The experimental evidence showed that the laminar turbulence transition is significantly delayed to higher Reynolds number when the body is heated. The purpose of the current study is to investigate the influence of viscosity stratification by wall heating on skin friction reduction in turbulent boundary layers. The results provide clear evidence that wall heating yields skin friction reduction. Also, the turbulence intensity and the Reynolds shear stress were decreased in the heated flows. In addition, both the mean scalar and the scalar fluctuation of the present flows were reduced relative to the constant viscosity configuration. In regards of the power required to heat the wall, it can be said that this method is practical and could be used. The only inconvenience will be that the study of the materials that you can use for this type of method for the aircraft. The next method will be moving surface. The method focuses on the lack of studies at low speeds in the implementation of a rotating cylinder that can improve the performance of the aerodynamic profile. It presents the study at low speeds and high Reynolds number using a symmetric and an asymmetric aerodynamic air profile, which they are NACA 0021 and NACA 23018, respectively, and comparing the results of these aerodynamic profiles with and without the rotating cylinder. With a moving surface, an attempt is made to delay the separation of the boundary layer from the wall by injecting an additional impulse into the boundary layer and preventing a growth of the boundary layer by decreasing relative movement between the surface and the free stream. In the present study, a moving surface boundary layer control is considered a method to improve aerodynamic characteristics and to delay the transonic change. A flow control was carried out considering a piece of the upper surface of an aerodynamic profile that will move with a constant speed. It is about delaying the transonic change because the transonic flight is characterized by the appearance of a local supersonic region on the side of suction from an aerodynamic profile, ended by shock. This shock leads to a loss of overall pressure resulting in additional drag. The results are shown by comparing lift and drag coefficient of the analyzed aerodynamic profiles These show that the computational results show positive results with the profiles that contain the rotating cylinder, but experimental results show that they cause a lot of vibration on the surface, and this caused negative results compared to when they did not have the rotating cylinder. This method is very practical but very difficult in the making. There are still research done for this method for the complexity of this type of designs and the vibration that they cause. The next method will be vortex generator. Vortex generators are commonly used in aircraft to improve the lift coefficient and drag coefficient. In this study, the vortexes generated from a modification in the form of the vortex generators is analyzed, which has already been investigated. The process is to analyze a NACA 0015 wing profile with and without the vortex generators using a wind tunnel. This is done because having upgraded knowledge about the vortices can have a greater control of the displacement of the boundary layer around an airfoil, and this brings many benefits to the aircraft. The results are shown by comparing the profiles with vortex and without vortex generators, and also comparing different AOA. In the low AOA, it is obtained that the drag coefficient increases rapidly and the presence of the vortex induces a modification of the movement of the detachment point of the flow, and their oscillations are inhibited. In the high AOA, in the outflow region, the detachment is thicker and the wake is deviated towards positive Y. As expected, through the inflow region, the flow is maintained attached to and thus large incidences can be achieved without stall occurrence. This is one of the most practical methods used for boundary layer control because of the simplicity of this method. In conclusion, we see that this area in aerodynamics is still in some improvements and getting new ideas to improve the boundary layer control. In this study, we mentioned some of the methods that are still in process of research and other ones that are already in use in some aircraft. So taking this into account, we can say that the most practical of these methods will be the vortex generator. For this, it might not be the most efficient one, but or that makes a really great change in the boundary layer control, but it is the simplest one that show an improvement in the delay of the detachment of the boundary layer. The second one might be the local heating of the wall. This method is also very practical for the simplicity, but the disadvantage is the type of materials that we need to use for this method, as expected, might not be the ones that are already in the aerospace industry. The other methods are also very acceptable. It's still in research, but they require some improvements for them to be used in an aircraft and to be efficient. So that's it. Thank you very much for watching. I hope you like this video.